Welcome students, this is lecture 6 of indefinite integration. In this class we will be looking up at integrals which have integrand of trigonometric nature. Now as a review we will start off with this particular question. So in the previous class we studied about solving integration problems using partial fractions. So if I were to rewrite this can be rewritten as integral dx over x times of, now x to the power of 4 negative 1. Now I can rewrite this as x squared negative 1 times x squared positive 1. This can be further rewritten as integral dx over x times x squared negative 1 can be rewritten as x negative 1 times x positive 1 times x squared positive 1. Now if I were to write this as using the concept of partial fractions, first what I will do, I will just consider the integrand, which is 1 over x times of x negative 1 times x positive 1 times x squared positive 1. This can be rewritten as a over x positive b over x negative 1 positive c over x positive 1 positive dx positive e over x squared positive 1. Now if I were to cross multiply, I would get a is equal to, in fact 1 is equal to a times of x negative 1 times x positive 1 times x squared positive 1 positive b times of x times x positive 1 times x squared positive 1 positive c times of x negative 1 times x squared positive 1 positive dx positive e of x times x negative 1 times x positive 1. So this is what we have got. Now what we will do is we will let me just take this as 2. Now let x be equal to 1. If I were to take x equal to 1, I would get this to be 0, this to be 0, and this will also be 0, right? Because x is equal to 1. And so what would be remaining is the terms involving b alone. In fact, even c will get vanished, and this entire term will also get vanished, and this is also off the charts. So we got b times of 1 times 1 positive 1 times 1 positive 1. This is rewritten as 1 positive 1 2. 2 times 2 is 4, so 4 times b, so therefore the value of b is 1 over 4, so that's fine. Now let me put x is equal to 0. If I were to take x is equal to 0 into, this is going to vanish, this will vanish, and x is equal to 0, this will also vanish because we got a x here. So this term vanishes, this term vanishes, this term vanishes, and we have got 1 is equal to a times of negative 1 positive 1 and 1, which would give us negative a, and therefore a is equal to negative 1. That is very good because we have already got two values, right? Now let me take x to be equal to, if I were to take x to be equal to negative 1, what would happen? My x would be, okay, this will vanish, x is equal to negative 1. Let me just take that value, x is equal to negative 1 in 2. So this is going to become equal to 0, and x is equal to negative 1, this will be 0, and this will be 0. So we got this going off, and this going off, but this will be there. So 1 is equal to c times of negative 1 and negative 1 negative 1, and this is positive 1 positive 1, which would give us negative 2 positive 2, and you have a 2 here, 4, so 4 times c, therefore c is equal to 1 over 4. So this is the value that we have got. So that is perfectly fine. We are already on the course of getting all of the values. So let me have a check one more time. Negative 2, negative 4, positive 4. Okay, that's fine. Now we need to get the value for d and e. So if I were to take x is equal to 2, if I were to take x is equal to 2, what would happen? I would get all of these values. So let me substitute x is equal to 2, because that's the only way we can get the value for D and E, because A, B and C were already obtained and we have got nothing else to substitute, so that the terms become 0. We have exhausted because we have taken already x is equal to 1, x is equal to -1 and x is equal to 0. So now we have to take a value apart from these values that we have already substituted in. So now I take x is equal to 2, so that's going to be 2 -1, 2 +1 and 2 squared +1, positive b times of 2 +1 times 2 squared is 4 +1, positive c times of 2 1 4 +1 is 5, and this is going to give me 2 times d positive e, 2 times 1 times 3. So this will be equal to, so a of 1 and 3 and 5, and this is going to be b of 2 and 3 and 5. This is going to be c of 2 and 5. This is going to be 6, so 6 into 2, 12d positive 6e. Now I know the value of a is -1, so this is going to be -15, and I got the value of b to be as 1 over 4, so that's going to be 15 over 2, and I've got the value of c to be as 1 over 4, that's going to be 5 over 2. Of course I've got a 12d and a 6e and a 1 here. So if I were to move this to the other side, this is going to be 1 positive 15, that's 16, and I can take the LCM as 2 here, that's going to be 20, positive 12d, positive 6e. So this is going to be 10, right? 2 will divide here 10 times, and 16 -10 is equal to 12d positive 6e. This is going to be 6 is equal to 12d positive 6e, and I can divide by 6, I'll get 1 is equal to 2 times d positive e. So this is the equation. So let me take it as equation 3. Now I want to take x to be equal to positive 3. I don't want to take x is equal to -2. If I want, I can take it, but I will take it as x is equal to positive 3. So let x be equal to 3 in 2. So that is going to give me, I'm substituting it in this system. Okay, so let me write that down here. So 1 is equal to a of x is equal to 3 -1, 3 positive 1, 3 3s are 9 positive 1, 10, positive b times of 3, 3 positive 1, 4, and a 10 positive c of 3, 3 -1 is 2, and a 10 positive 3 times d positive e of 3, and a 2 and 3 positive 1 as 4. So that's fine. So 1 is equal to, this is going to give me a of 2, 3, 1, 4 and 10. 3 times 4 is 12, 12 times 10, 120 times b, 3 times 2, 6, 60c, and 3 times 2, 6, 6 4s are 24 times 3d positive e. So a is -1, right? So if I have to substitute here, 4 times or 2 times 4, 8, 8 times 10, 80, -80, and b is 1 over 4, and this would give me 30, and c is 1 over 4, and this would give me 15, and positive 24 times 3, so 3 4s are 12, 1 3 2 are 6, 72d positive 24e. This is what I've got. I got a 1 here. Now if I were to add these two, this would give me negative 50. Negative 50 added with positive 15. So that's going to be 10. 5, 4, from 4 I take away 1, I get 3 with a negative sign. So that's going to be negative 34. I move to the other side, that's going to be 36. This is going to be 72d positive 24e. So this is what I've got. Now if I were to use 6 divides here 6 times, 6 divides here 12 times, 6 2s are 12, 1, and that's fine, and 6 divides here 4 times. So I've got an equation here, so this is 4. Now I'm going to solve 3 and 4. Solving 3 and 4 we get, so what do we get? I'm going to write it like this: 2d positive e is equal to 1, and this is 12d positive 4e is equal to 6. This is 3, this is 4, this is 12d. So now what I wish to do, I will multiply 3 with 6. So that is going to give me 6 with 2, that's going to be 12. 12d positive 6 times e is equal to 6. And this is already 12d, and 4 times e is equal to 6. So if I were to subtract this, this one will give me 2 times e. Right, these two will get cancelled. So this is 6e negative 4e will be 2e, 6e minus 6e will be 0. Therefore e is equal to 0. Now if e is equal to 0, put in 3. So that means 2d positive e is equal to 0 is equal to 1. So 2d is equal to 1, therefore d is equal to 1 over 2. So that's fine. Even if I were to substitute e is equal to 0, this will be, d will give me 1 over 2. So I've got the value for d and I got the value for e. So let me write them down. So therefore, well, let me put that down. A is negative 1, b is 1 over 4, c is 1 over 4, and my d is 1 over 2, and my e is 0. So therefore the integration is integration of dx over x times x to the power of 4 negative 1 is rewritten as, I am using the partial fractions, which is over here, right? If I take this as 1, I'm going to substitute the value of a, b, c, d, e. So that would give me negative 1 over x, positive 1 over 4 times x negative 1, positive 1 over 4 times x positive 1, positive 1 over 2 times x over x squared positive 1. My e is 0, so that goes off. So this is what I've got. So if I were to rewrite this, it's going to be negative integral dx over x, positive integral 1 over 4 dx over x negative 1, 1 over 4 integral dx over x positive 1. This is 1 over 2 times x over x squared positive 1 times dx. Now all of these integrals can easily be obtained, but for this I'm going to take x squared positive 1 is equal to t, so that's going to be 2x dx is equal to dt. So from here dx is equal to dt over 2. So if I were to substitute it here, x dx over x squared positive 1 will be dt over 2, x squared positive 1 is going to be t, so this is going to be half times ln t. But there is already a 1 over 2 here, so we will have to substitute it there. So if we have to substitute it 1 over 2 with 1 over 2, that is going to be 1 over 4. 1 over 2 times 1 over 2, 1 over 4, and my ln t, my t is x squared positive 1, so that's going to be x squared positive 1, so that's fine. And this is going to give me negative ln x, this is going to give me 1 over 4 ln of x negative 1, and this is going to give me 1 over 4 ln of x positive 1. So this is the result. However, we can rearrange them. See, for example, we can take 1 over 4, 1 over 4 out. In fact, I've got 1 over 4, 1 over 4 all through. So if I were to take 1 over 4 out, this is going to give me ln of A positive B positive C. So I can rewrite this as x negative 1 times x positive 1 times x squared positive 1, right? And you got a negative ln x. And this can be further rewritten as 1 over 4 times A ln A B C, or it's going to be ln A B C, because you got a product here. So this is going to be x negative 1 times x positive 1 will give you x squared negative 1. You got a x squared positive 1. This is actually x squared negative 1 multiplied with x squared positive 1. That's going to be x power 4 negative 1. So you got ln of x to the power of 4 negative 1. So this is what you got. Now you got a negative ln x. So I can place that negative ln x over here, right? So this is nothing but ln A minus ln B. In fact, I can take this 1 over 4 to the other side. But I think I can, I will stop over here. If you want, you can make the substitution, or I should say make the simplification still further using logarithmic properties, but I will just place the arbitrary constant c and I will draw the red line. Right now, a very important point. Now this is how we will have to handle a question involving a problem of this nature, but having given you the solution, I want to give you the alternate or the aliter to this particular question, which we will see now. Now students, I'm going to get the same result which I have just obtained by partial fractions for this integral. Let me use this space here, but I'm going to use a different technique. So you see the amount of space that would be required for getting the solution in comparison to the amount of space that we had taken in handling this question using partial fractions. So what I wish to do, we've been given this integral dx over x of x raised to the power of 4 negative 1. Now what I'm going to do, I'm going to place x cubed in the numerator, and I'm going to have x to the power of 4 in the denominator. So clearly x to the power of 3 will divide x to the power of 4, giving me x. So that's fair enough. So I'm going to retain x to the power of 4 negative 1 as it is. Now what I will do is I will use a substitution technique. Let x raised to the power of 4 be equal to t, right? 4 times x to the power of 3 times dx is equal to dt. I'll push the 4 down. So that would give me x cubed dx is equal to dt over 4. So in place of x cubed dx, I'm going to substitute dt over 4. So this is going to be integral dt 1 over 4 can be taken out, divided by, in place of x to the power of 4 it's going to be t, in place of x to the power of 4 is going to be t followed by a negative 1. Now the numerator has got 1. Now what I wish to do is I'm going to rewrite 1 as t negative of t negative 1. If you were to distribute this negative sign, you will get t negative t, so t and t gets cancelled. Negative times negative will be 1. So we are getting back the left hand side. So now what happens is we need to replace 1 by t negative of t negative 1. So this is how we will do it. So I'm just going to substitute t negative of t negative 1 times dt divided by t of t negative 1, right? Now I need some space, so let me just use the space that is present over here. So starting with, I've got integral of t negative of t negative 1 times dt divided by, the denominator is t of t negative 1. So I can split this as t times dt over t of t negative 1 followed by a negative sign, and t negative 1 over t of t negative 1 times dt. So clearly t can be cancelled here, t negative 1 can be cancelled here. So you get Of course, this entire quantity has got 1 over 4. You see that? 1 over 4. We shouldn't forget that 1 over 4. So that has to be placed here. 1 over 4. So I got a 1 over 4, 1 over 4. So let me rewrite this as 1 over 4 times integral dt over t negative 1 followed by a negative sign integral dt over t. Now integral of dt over t minus 1, that's going to be ln of t negative 1. Of course there's a 1 over 4 there, followed by a negative of ln of t. But my t, what is my t? My t is x to the power of 4. So substitute that value. So this can be rewritten as ln of x to the power of 4 negative 1 is equal to 1 over 4 followed by a negative ln of x to the power of 4. Positive arbitrary constancy. But is this the result that we got? See, the result is 1 over 4 times ln of x to the power of 4 negative 1. This is what we have got. One component followed by a negative ln x positive c. We need to have a parenthesis here, of course, because that is clearly understandable, right? Because it's going to be a product multiple of this entire component. So now this is actually the original result what we have got in the previous case. Because if I were to use ln a raised to the power of b is equal to b times ln a, if I were to do that, this is equal to 1 over 4 times ln x power 4 negative 1 followed by negative 1 over 4 times ln of a raised to the power of b is nothing but b times ln a. So it's going to be 4 times ln x positive arbitrary constancy. So clearly I can get rid of this 4, which would give me 1 over 4 times ln of x to the power of 4 negative 1 negative ln x positive c, right? So this is exactly what we have got in partial fractions. You see that? So that is a beautiful question, and we will move on to the next question. So I have demonstrated two techniques by which we can solve this question, and this is also very important, using partial fractions. And having mentioned this, we will move on to the next question. Students, as I mentioned to you, in this class we will be dealing with integrals of trigonometric functions of the form integral dx over a positive b times sine squared x, integral dx over a times b cos squared x, integral dx over a times sine squared x positive b times cos squared x positive c times sin x cos x, and integral of type dx over a times cos x positive b times sin x raised to the power of 2. So whenever you see any of these forms that I have shown here, what you have to do is you will have to multiply the numerator and the denominator either by secant squared x or by cosecant squared x. So either you can multiply the numerator and the denominator by secant squared x or by cosecant squared x. So that is the keynote, and the integral that you are looking for should be one of these types. So having mentioned this, we will do a question to achieve better understanding. So let's solve this question. We've been asked to obtain the integral of dx over 4 negative 5 times sine squared x. So as I mentioned to you, this is of this form that we have just seen here, and in that case we will have to multiply the numerator and the denominator either by secant squared x or by cosecant squared x. Now I want to choose cosecant squared x for the very fact that I see a sine squared x here. So let us multiplying the numerator and the denominator by cosecant squared x, we get, so So what do we get? So this is equal to numerator cosecant squared x times dx over 4 times cosecant squared x negative. Now if I were to multiply by cosecant squared x sine squared x, cosecant squared x is 1 over sine squared x. So that would mean the sine squared x and the sine squared x in the denominator will get neutralized, giving us 5. So this is what we have got. Now we know that cosecant squared x negative cot squared x is equal to 1. So therefore cosecant squared x is equal to 1 positive cot squared x. So I'm going to substitute that here. So this is equal to integral cosecant squared x times dx over 4 times of 1 positive cot squared x negative 5. Now let me take cot x to be equal to 2. I differentiate this, I get negative cosecant squared x dx is equal to dt. So this would mean cosecant squared x dx is equal to negative dt. So I substitute the value here. So it's going to be integral negative dt for cosecant squared x dx divided by 4 times of 1 positive cot x is t, so it's going to be t squared there followed by a negative sign. So this is equal to negative of dt over 4 positive 4 times t squared negative 5. This is going to give me negative of dt over 4t squared negative 5. So what I can do is I can take 4 out. So that's going to be negative 1 over 4 integral dt over t squared negative. In fact, I can actually, in fact this is not negative 5 because 4 added with negative 5 would give me negative 1 here, right? So this is going to be negative 1 over 4. So I'm going to rewrite this as negative 1 over 4 integral dt over t squared. 1 over 4 I can write it as 1 over 2 squared. Now there is a formula we know. We know that integral dx over x squared negative a squared is equal to 1 over 2a ln of x negative a over x positive a, positive arbitrary constant c. So by this formula this is equal to 1 over 2a. So my a is 1 over 2. So 1 over 2 times my a is 1 over 2, that's fine, times ln of my x is t negative, my a is 1 over 2 divided by t positive 1 over 2. I'm not placing the arbitrary constant as yet. So now what happens? The 2 and the 2 can be cancelled here. So that's going to give me 1. So it's going to be negative 1 over 4 times ln of my t. What is my t? My t is, let us simplify this first, okay? So this is going to be 2 times t negative 1 divided by 2, but that 2 will get cancelled with the 2 that will be resulting here. So it's going to be 2t positive 1, and if I were to substitute the value of t, t is cot x. So this is going to be rewritten as negative 1 over 4 ln of 2 times cot x negative 1 over 2 times cot x positive 1, positive arbitrary constant c, and that is a good place for us to draw the red line. So this is a beautiful question, students. It needs some care, and with that little bit of practice we will be able to achieve it. So practice makes it imperative, or I should say practice is necessary. So I would like to suggest you all to practice and more practice. Students, now I will introduce type 2 in integrating trigonometric functions. So this is going to be type 2. Now in type 2 the trigonometric functions will be of linear nature. In type 1 they were of quadratic nature. In type 2 they will be of linear nature. So the form would be integral dx over a positive b times sine x, so this will be of one form, or it would also be of this form, a positive b times cos x, or it would be of this form, integral dx over a positive b times sine x positive c times cos x. In either of these forms, we will have to convert the sine x and cos x to their respective tangent of angles. Okay, tangent of angles. So what exactly it means, tangent of angles? Let me write that down. Of angles. Right, now the meaning is we will have to give their equivalent representation in tangent of angles for sin x as well as for cos x. So that would mean sin x would be rewritten as 2 times tan of x over 2 divided by 1 positive tan squared x over 2. So this is for tan x, sin x, and for cos x it would be 1 negative tan squared x over 2 divided by 1 positive tan squared x over 2. So this is the standard conversion that we will have to apply, and you will get a better understanding when I give you an example to illustrate this type 2. So students, to understand this concept, let us do an example. So I'm going to take this question. We are expected to integrate integral dx over 5 positive 4 times cos x. So this is a linear system in the denominator, and it is trigonometric in nature. So what I would do is I will take cos x to be equal to 1 negative tan squared x over 2 divided by 1 positive tan squared x over 2. So therefore the original integral can be rewritten as dx over 5 positive 4 times of 1 negative tan squared x over 2 divided by 1 positive tan squared x over 2. Now this is rewritten as, if I were to take the LCM, this is going to be 5 times of 1 positive tan squared x over 2 positive 4 times of 1 negative tan squared x over 2 divided by 1 positive tan squared x over 2, and you got a dx there. If I were to flip it, this can be rewritten as integral 1 positive tan squared x over 2 times dx divided by, I'm distributing the quantities of 5 and 4, so that would give me 5 positive 5 times tan squared x over 2 positive 4 negative 4 times tan squared x over 2. So 5 times tan squared x over 2 added with 4 times tan squared x over 2 would give us, in fact there is a negative sign here, right? So taking that into account, that will produce us a tan squared x over 2. So this is equal to, now we know that secant squared x negative tan squared x is equal to 1, and secant squared x is equal to 1 positive tan squared x. We know this formula. So using that formula, this is going to be secant squared x over 2 divided by 5 added with 4, that's 9. 5 times tan squared x over 2 added with negative 4 times tan squared x over 2 would give us positive tan squared x over 2. Of course there is a dx there. Now in all these cases, the type involving the nature which I've just discussed in the start of the question, you will have to make the substitution as follows, that is tan x over 2 to be equal to t. This is a standard substitution, and remember this. If I were to differentiate this, this is going to give me secant squared x over 2. The coefficient of x is 1 over 2, so multiply that, followed by a dx and a dt. Move this 2 to the right hand side, that would give us secant squared x over 2 dx to be equal to 2 times dt. So now what we can do, we can take the value for secant squared x over 2 dx as 2 times dt. So this is equal to 2 times of integral dt divided by 9 positive tan x over 2 is t, so this is going to be t squared. I can rewrite this as integral dt over t squared positive 3 squared, which is the famous formula, right? Integral dx over x squared positive a squared, which is equal to 1 over a tan inverse of x over a, right? So using this formula, so that upon integration would give us 2 over 3 tan inverse of x over a, so tan inverse of t over 3, but my t is tan of x over 2, so that would give us 2 over 3 tan inverse of tan of x over 2, that has to be divided by 3 positive arbitrary constant c, and that is a good place for us to draw the red line. So we'll move on to the next question. Now I'm going to show you a shortcut. For that we will have to again resort to substitution, but this is going to be a substitution of a different type. Now we have got this question, right? Integral dx over 5 positive 4 times cos x. Now we would be able to achieve the solution if and only if we make the substitution for tan of x over 2 to be equal to t and convert this quantity that we see here to t. But with the following substitution we can directly achieve this stage or this particular step. So how is it done? Now whenever you got, or in place of dx, we make the substitution as 2 times dt. This is a shortcut, but this should not be taken to be as a hard and fast rule. So this is just a shortcut. So shortcut will always have their own pitfalls. So having mentioned that, I am still bringing it to your knowledge or to your observation from awareness point of view. So having said that, in place of dx we substitute 2 times dt. In place, suppose you got sin x, we will have to make the substitution as 2t, and if you got 1, we will make the substitution as 1 positive t squared, and if you got cos x, we will make the substitution as 1 negative t squared. So have this in mind. So with that, I am going to rewrite dx as 2 times dt, and 5 is actually 5 times 1, right? So in place of 5, I shouldn't say in place of 5 is written as 5 times 1, so there is a 1 there, so that would mean I will place a parenthesis and write 1 positive t squared followed by 4 times of cos x is 1 negative t squared, right? So if you were to simplify this, this is going to give me 2 times of integral dt over 5 positive 5 times t squared positive 4 negative 4 times t squared. This is equal to 2 times integral dt over 5 positive 4 is 9, 5t squared negative 4t squared will give me positive t squared. This is nothing but 2 times integral dt over, now I can rewrite this as t squared positive 3 squared. This is exactly what we have got, and this is nothing but shortcut. Okay, now to prove the shortcut I'm going to do another question. So this is question number 2. We are expected to integrate integral dx over sin x negative 3 times cos x negative 1. Now I will do by the long method and I will also do by the short method. So long method, we are to replace sin x by the following substitution. So 2 tan x over 2 divided by 1 positive tan squared x over 2, and our cos x is going to be 1 negative tan squared x over 2 divided by 1 positive tan squared x over 2, right? So I'm going to make the substitution there. So this is going to be integral dx over 2 times tan x over 2 divided by 1 positive tan squared x over 2 negative 3 times of 1 negative tan squared x over 2 divided by 1 positive tan squared x over 2, and you got a negative 1 there. So this is rewritten as, let me use the space here, integral dx over, I'm taking the LCM as 1 positive tan squared x over 2 that will give me 2 times tan x over 2 negative 3 and positive 3 times tan squared x over 2, and since one positive tan squared x over 2 is LCM, this is going to give me negative 1 and negative tan squared x over 2. So this is what I've got. Now what I can do is I can add 3 times tan squared x over 2 with negative tan squared x over 2 and negative 3 with negative 1. So if I were to flip this, this will go to the numerator. So this is going to be integral 1 positive tan squared x over 2 divided by, this is going to give me 2 times tan squared x over 2. There is 2 times tan x over 2 and there is negative 4 there, right? So this is what I have got here. Of course we need to place the dx there. Now we know the formula that secant squared x negative tan squared x is equal to 1. So from here secant squared x is equal to 1 positive tan squared x. So I need to use this space. So this is going to be secant squared x over 2. So that's equal to integral secant squared x over 2 times dx divided by 2 times tan squared x over 2 positive 2 times tan x over 2 and then you got a negative 4. Now let me make the substitution. Tan x over 2 be equal to t. This is secant squared x over 2. There is a coefficient for x, that's 1 over 2, and you got a dx, you got a dt there. So secant squared x over 2 dx is equal to 2 times dt. So substitute this value there. So this is 2 times dt divided by 2 times t squared positive 2 times t negative 4. So this is a quadratic. If I were to take 2 out, this is going to be 2 times of t squared positive t negative 4. 2 can be negative 2. This is 2 and 2 can be cancelled, giving me integral dt over t squared positive t negative 2. Now I'm going to rewrite this t squared positive t negative 2 as a perfect square. That's going to be t positive 1 over 2 raised to the power of 2. Now if I were to square this, I would get t squared, then 2 times t, then I will have a positive 1 over 4. Now I don't want that, I have to remove that positive 1 over 4. So to get rid of the positive 1 over 4, I place a negative 1 over 4 here, right? Of course there's a negative 2 there. So this is rewritten as t positive 1 over 2 raised to the power of 2. If I were to simplify, and in fact I'm taking the LCM, so that would give me negative 1 and 8, so negative 9 over 4. So this can be rewritten as t positive 1 over 2 squared negative 3 over 2 squared. So x squared negative a squared. So this is equal to integral dt over t positive 1 over 2 raised to the power of 2 negative 3 over 2 whole squared. Now this is, we know a formula. What is the formula? We know that integral dx over x squared negative a squared is 1 over 2a ln of x negative a divided by x positive a, positive arbitrary constancy. So I'm going to use that formula here. So this is my x, this is my a. So it's going to be 1 over 2 times my a is 3 over 2, right, times ln of my x is t positive 1 over 2 minus, this is my x, minus my a is 3 over 2 divided by t positive 1 over 2 plus 3 over 2. So I'm not placing the arbitrary constant as yet. Let me simplify this. So this is 1 over 3 ln of, if I were to take the LCM, this is going to give me 1 over 2. So I got a t here and I got a 1 over 2 and a negative 3 over 2. That's going to be negative 2 is negative 1. So this is negative 1, right, divided by, and I got 1 over 2 and 3 over 2, that's 2. So it's going to be t positive 2. But my t is tan of x over 2. So substitute that value there. So this is going to be 1 over 3 ln of tan x over 2 negative 1 divided by tan x over 2 positive 2, positive arbitrary constant c. So this is the solution for the question. Now to appreciate the shortcut, so let me write that problem down. I'm going to use this particular space here. The problem is integral dx over sin x negative 3 times cos x negative 1. So I'm going to use the shortcut. In place of dx, it's going to be 2 times dt. In place of sin x, we will have to substitute 2 times t. In place of cos x, we will have to substitute 1 negative t squared, and in place of 1, we will have to substitute 1 positive t squared. So if we have to simplify this is going to be 2 times integral dt of, this will give me 2t negative 3 positive 3 times t squared negative 1 negative t squared. This is equal to 2 times integral dt over 3 times t squared with a negative t squared will give me 2 times t squared, and I've got a positive 2t, and negative 3 negative 1 will give me negative 4. This is what I've got. Now just see here. Just see here. See this point. Are you seeing it? So with the shortcut, I don't have to do any of this. You see the steps I have done here? See the steps? So many steps I've done here. And if you were to make a single mistake anywhere, you would not get the answer. You will not get the answer. So this answer which we have got is absolutely correct, because of the very fact from the shortcut I'm getting the same system. You see that? The same system is obtained. Now, as I mentioned to you, you have to be careful when you are performing these stages, and extreme measures and extreme efficiencies has to be executed, or I should say implemented. So we'll move on to the next question. Since this is the third type of integrals involving trigonometric functions, and to solve this there is a special technique. So let me write down the question for this. So you are given a question of this nature: sin x negative, or I should say positive 3 times cos x positive 1 divided by sin x negative 3 times cos x negative 1 times dx. So this is what you have been given, and you got two quantities here, numerator and the denominator. Now take the numerator, sin x positive 3 times cos x positive 1, and this numerator is expressed as a times the denominator, sin x negative 3 times cos x negative 1 positive b times the differential of this denominator, that's going to be cos x. Differential of cos x is negative sin x, so that's going to be positive 3 times sin x, and the differentiation of negative 1 will be 0, positive c. So this is the standard form that you will have to follow whenever you've been given a question of this type. So now what I'm going to do, I'm going to take the coefficients of sin x and cos x and constant term together. So how would I do that? Over here I get a times sin x and 3 times b sin x. So this is going to be a positive 3 times b with sin x. So as I mentioned to you, we are gathering the coefficient of sin x and cos x together. Now in cos x it's going to be 3 times a with a negative sign and b. So this is going to be negative 3 times a positive b times cos x. That's fine. Now constant term, what is the constant term? A times negative 1, so negative a. There is no constant term for b, so that has to be followed with c. Now on the left hand side we got sin x positive 3 times cos x, positive 1. So equating the coefficient of sin x, on the left side you get 1, on the right side you get a positive 3b. That's one equation. Equating the coefficient of cos x, you get 3 here, and on this side you get negative 3a positive b. Equating the constant term, you get 1 is equal to negative a positive c. So we can solve. Let me take this as 2, 3 and 4. So what I'm going to do, I'm going to multiply 2 with 3. So that would give me 3 is equal to 3 times a positive 9b, and I'm going to solve it with equation 3. So we're going to be 3 negative 3a positive b. So you can cancel these two things. So this is going to be 6 and this is going to be 10b. Therefore b is equal to 6 over 10 and 3 over 5. So the value of b is 3 over 5. I got the value for b, and if I were to substitute the value of b in, put b is equal to 3 over 5 in 2, that would give me 1 is equal to a positive 3 of 3 over 5, which is going to be a positive 9 over 5, which is nothing but 1 negative 9 over 5 is equal to a. So therefore a will be negative 4 over 5. So a is 4 over 5. The value of c is what? Put a is equal to negative 4 over 5 in 4. So 1 negative of negative 4 over 5 positive c. This is going to be 4 over 5 positive c. Therefore 1 negative 4 over 5 is equal to c. So c is equal to 1 over 5. So I've got the value of a, b and c. So in place of this quantity numerator, I will have to substitute this. So students, having obtained the value for a, b and c, what we need to do now is to take these values and substitute them in, say, 2. That's exactly what I'm going to do, and that would mean the numerator which we have just taken here would now be represented with the terms that you can see on the right hand side. So now the integral is rewritten as integral. In place of a, it's going to be negative 4 over 5 times, I'm actually substituting the values for a, b and c, and the numerator would be represented in this fashion. So that's going to be sin x negative 3 times cos x negative 1, and the value for b is 3 over 5 of cos x positive 3 times sin x positive. The value for c is 1 over 5. So this has to be divided by the denominator, which is sin x negative 3 times cos x negative 1, and this entire quantity has to be multiplied by dx. Now I'm going to use algebraic property. A positive b over c is a over c positive b over c. So with that I can rewrite these terms as 4 over 5 integral this quantity over the denominator, sin x negative 3 times cos x negative 1 times dx divided by sin x negative 3 times cos x negative 1 positive 3 over 5 times integral cos x positive 3 times sin x times dx divided by sin x negative 3 times cos x negative 1 positive 1 over 5 times integral dx over sin x negative 3 times cos x negative 1. So now clearly we can cancel the terms here, and this is going to be negative 4 over 5 integral of dx positive. Now this quantity, let me just use this space here. if I were to take, let sin x negative 3 times cos x negative 1 is equal to t, differentiating this would give me cos x positive 3 times sin x times the dx is equal to dt. So in place of the numerator I can place dt, in place of the denominator it's going to be t, so this is going to be ln t, and that is nothing but ln of sin x negative 3 times cos x negative 1. So that's exactly what I'm going to be placing there. So with 3 over 5 times ln of sin x negative 3 times cos x negative 1 positive. Now we will have to integrate 1 over 5 times dx over sin x negative 3 times cos x negative 1. Now to integrate this, I have given you a shortcut in the previous question, but anyway what I will do is I will try to do the integral over here. So let me just consider, I'm going to use this space here, let me just consider integral dx over sin x negative 3 times cos x negative 1. So in place of dx we will substitute the following. So this is going to be 2 times dt. In place of sin x we will substitute 2t. In place of cos x is going to be 1 minus t squared. In place of 1 is going to be 1 positive t squared. So these are the substitutions that will go into the problem. So this is actually the shortcut, but the long way I have already done it in the previous question, so you can just check that out. So this can be rewritten as, in place of dx is going to be 2 times dt. In place of sin x it's going to be 2t. In place of cos x it's 1 negative t squared. In place of 1 it's 1 positive t squared. So this is equal to 2 times integral dt over 2t negative 3 positive 3 times t squared negative 1 negative t squared. So I can add 3t squared with t squared, so that's going to give me 2 times t squared. And is there anything else I can add followed by 2t and negative 3 and negative 1? That would give me a negative 4 there. So if I were to, because this is producing a negative 3, this is giving me a negative 1, so that's fair enough. So this is going to be 2 times of integral. I can take a 2 out. If I were to do that, it's going to be t squared positive t, and in fact I can take a 2 out completely, so it's going to be negative 2 here. So this 2 and 2 gets cancelled. So what I have got here is, let me use the space here, I've got integral dt over t squared positive t negative 2. This is what I've got. Now this can be rewritten as integral dt of t positive 1 over 2 raised to the power of 2 negative 3 over 2 raised to the power of 2. Right? Because I have already shown you how to write it as a square of 2 terms in the previous problem, so you can check that out. Now this is very much similar to integral dx over x squared negative a squared, which has a formula of 1 over 2a log of x negative a over x positive a, positive arbitrary constant c. So if I were to use that, this is going to be 1 over 2 times a is 3 over 2 ln of my x is t positive 1 over 2, right, negative my a is 3 over 2 divided by t positive 1 over 2 positive 3 over 2. So we have to do some simplification. So this is equal to 2 gets cancelled, this will be 1 over 3 Now I can add 1 over 2 with negative 3, so that's going to give me negative 2 over 2, so it's going to be negative 1. So this is going to be ln of t negative 1 divided by t positive 2. So 1 over 2 added with 3 over 2 would give me 4 over 2. That's going to be 2. So this is for my t. But my t is tan of x over 2. Right? This is the standard substitution. So we will have to substitute that quantity here. Okay? You will have to refer the previous question. So now with this substitution, the solution would be completed. So what would be the solution? So let me write the solution over here. Of course, this is what we have got. Clearly we know that this is equal to negative 4 over 5 integral of dx is going to give me x. So it's going to be negative 4 over 5 times x. Positive 3 over 5 times ln of sin x negative 3 times cos x negative 1, that's fine, plus 1 over 5 times, of course there is a 1 over 3 here, so that multiplied with 1 over 5 would give you 1 over 15. So it's going to be ln of, in place of t, substitute tan x over 2 negative 1 followed by tan x over 2 positive 2. So this is the solution with the arbitrary constant c. Of course it is a little bit compressed because of the lack of space, and I hope you would have got a gist of this question. If you would have followed this question step by step, you wouldn't have any issues at all, because you can always rewind and review this particular question, and it's a beautiful question, students. So we will move on to the next question. Integrals. This is of the form x squared positive 1 over x to the power of 4 positive k times x squared positive 1 times dx. And you can also encounter a form of this fashion, x squared negative 1 over x to the power of 4 positive k times x squared positive 1 times dx. Now in either of these cases we will have to take x squared as a common factor from the numerator and denominator and perform appropriate substitution technique. So that is the idea. Now the best way to understand this is through a question. So I'm going to be solving this question. We have been given x squared positive 1 over x to the power of 4 positive 7 times x squared positive 1 times dx. This is of the form x squared positive 1 over x to the power of 4 positive k times x squared positive 1. So what I wish to do is I would like to take x squared out. So that would give me 1 positive 1 over x squared times dx divided by x squared is taken out. So this is going to be x squared positive 7 positive 1 over x to the power of 2. Now x squared and x squared can be cancelled. This is going to give me 1 positive 1 over x squared divided by x squared positive 7 positive 1 over x squared times dx. Now this is the idea. Now if you get in the numerator 1 positive 1 over x squared, then you have to express the denominator using x negative 1 over x. So this is the keyword. So you should express the denominator using x negative 1 over x. On the other end, so this is case 1. Now you got case 2. Now if you have the numerator to be of the form 1 negative 1 over x squared, then you should express the denominator using x positive 1 over x. So in this case the numerator has got 1 positive 1 over x squared. So I'm going to express the denominator x squared positive 7 positive 1 over x squared using x negative 1 over x. So if I were to substitute or replace this quantity with x negative 1 over x raised to the power of 2, upon expansion you can clearly see that this would produce the first term, x squared positive 1 over x raised to the power of 2. That will produce this term, x squared. But when you take 2ab, that is negative 2ab, you will have your negative 2 times of x times 1 over x. That's going to give you negative 2, right? So that is going to be coming here. Now if you were to get rid of this negative 2 in such a way that that cancellation which you are performing should ensure that we are able to get positive 7. So clearly from here, if I were to expand this, I would get x squared positive 1 over x squared negative 2. Now to get rid of the negative 2, what I need to do, I need to place a positive 2. So that negative 2 is already neutralized. But I need to have a 7 here. So for that I need to add 7. So if you were to compare the left hand side with the right hand side, they both agree, isn't it? And this can be further rewritten as x negative 1 over x raised to the power of 2 positive 9. Fair enough. So therefore what happens, this particular quantity, let me take it as 2. I can rewrite 2 as integral 1 positive 1 over x squared divided by x negative 1 over x raised to the power of 2 positive 9, and this is operated on, or I should say multiplied with the differential operator dx. Now let me make the substitution. Let x negative 1 over x be equal to t. If I differentiate this, I get 1. If I differentiate this, I get 1 over x squared with a positive sign times dx is equal to dt. So this is what is the outcome. Now clearly you can see that this is exactly what is featured in the numerator. So in the place of the numerator, I am going to replace it with dt. In place of the denominator, it's going to be t squared positive 9. Now I can rewrite this as dt over t squared positive 3 squared. Now we know a formula. What is that? Integral dx over x squared positive a squared is 1 over a tan inverse of x over a positive c. So by this formula, this is 1 over a is 3 tan inverse of x over a, right? Which is nothing but 1 over 3 times tan inverse of, my t is this quantity, right? X negative 1 over x, that's my t, and this has to be divided by 3, and that has to be added with an arbitrary constant c. So this is our solution, and it's a good place for us to draw the red line. So student, now let me give you a second example to show the second type which I've just represented here. So we will do an example to understand that. So we've been given here integral x squared negative 1 over x to the power of 4 positive x squared positive 1 times dx. So foremost I will take x squared out, so that's going to give me 1 negative 1 over x squared times, in fact divided by, I'm taking x squared out, so this is going to be x squared positive 1 over x squared times dx. So clearly the x squared can be cancelled, giving me integral of 1 negative 1 over x squared times dx divided by x squared positive 1 over x squared. Now clearly you can see the numerator is 1 negative 1 over x squared. So let's go back to the cases that I have mentioned. If you are having a numerator which has got 1 negative 1 over x squared, then express the denominator using x positive 1 over x. So that's exactly what I'm going to do. So this is equal to integral 1 negative 1 over x times dx. The denominator is expressed with x positive 1 over x raised to the power of 2. When I square it, I get the first term, and I square this term, I get the third term, plus 2 times of x. So that would mean I have an extra 2 which has to be removed. So I need to place a negative 1 here. So that's fair enough. So since that I've got the perfect integrand, I'm going to make the substitution. So the substitution is, let x positive 1 over x is equal to t. So if you were to differentiate this, you get 1. Differential of this would give you negative 1 over, this is actually x squared. Okay, so this has to be multiplied with dx, so that's going to be equal to dt. So this is exactly what is seen here. So if I were to substitute the quantity, in place of 1 negative 1 over x squared times dx, I am going to place dt. In place of x positive 1 over x raised to the power of 2, I am going to substitute t. That has to be raised to the power of 2 followed by a negative 1. I am going to write 1 as 1 squared. Now we know a formula. What is that? We know integral dx over x squared negative a squared is equal to 1 over 2a ln of x negative a over x positive a, positive arbitrary constant c. Now using this formula, this is equal to 1 over 2 times of a times ln of t negative 1 over t positive 1. But this is equal to 1 over 2 ln of my t. My t is x positive 1 over x. So substitute that, x positive 1 over x negative 1 divided by x positive 1 over x positive 1. So this is what we have got, and we have to place the arbitrary constant c, and this is a good place for us to draw the red line. So I have demonstrated 2 problems for these 2 cases, or for these 2 types which I have just mentioned. So we'll move on to the next question, students. Students, this is a beautiful question. We've been expected to integrate x raised to the power of x times x raised to the power of 2x positive 1 times 1 positive ln x over x raised to the power of 4x positive 1, and that has to be multiplied with the differential operator dx. Now the very first glance at this question would really take most students by surprise. In fact, even people who are doing calculus or who have completed calculus, because this needs a lot of practice and understanding, because this involves 2-3 types within it. So foremost, we would like to convert this by integration by substitution. So what I will do is, I'm going to make this substitution. So let x raised to the power of x be equal to t. When I differentiate this, I get x raised to the power of x times 1 positive ln x times dx is equal to dt. I've already shown you how to differentiate x raised to the power of x in the previous classes. So this is what we have got. Now clearly we can see that x raised to the power of x times 1 positive ln x dx is actually dt. So let us replace that. So this is equal to, now x raised to the power of 2x, now that is going to be rewritten as, this is what we have got here, right? I can always write this as x raised to the power of x raised to the power of 2. And x raised to the power of 4x, I can always write it as x raised to the power of x raised to the power of 4. So this is actually for your understanding, so that you can keep track of the substitution. So I'm going to first rewrite this as x raised to the power of x raised to the power of 2 positive 1 times, I'm going to club this, x raised to the power of x times 1 positive ln x times dx divided by x raised to the power of x raised to the power of 4 positive 1. So upon substitution, this is going to be x raised to the power of x is t, so this is t squared positive 1, x raised to the power of x times 1 positive ln x times dx, this is going to be dt, divided by x raised to the power of x, this is going to be t raised to the power of 4 positive 1. Now this is the type which I have just mentioned to you in the previous problem. So what we need to do is we need to take t squared out. So if we were to take t squared out, this is going to be 1 positive 1 over t squared times dt divided by, I'm taking t squared out, so this is going to be t squared positive 1 over t squared. So clearly the t squared that you see here can be cancelled. Now I've got a quantity in the numerator which is 1 positive 1 over t squared times dt divided by denominator t squared positive 1 over t squared. Now in the cases which I've studied, if you were to have a numerator which features 1 positive 1 over t squared, then you will have to rewrite the denominator using t negative 1 over t, right? That's exactly what we are going to do. So this is equal to integral 1 positive 1 over t squared times dt divided by t negative 1 over t raised to the power of 2. Now if you were to expand this, this will give you t squared positive 1 over t raised to the power of 2. So two terms are there. Now it will also give us negative 2, right? Because of 2ab, that's negative 2ab. So I need to get rid of the 2. So that is possible only when I add positive 2 here, right? So fair enough. So now what I'm going to do, I'm going to make the substitution. I'm going to state here, let t negative 1 over t be equal to sum p. So that would mean I can differentiate the left hand side, which would give me negative of negative. That's going to be positive 1 over t squared times dt is equal to dp. So clearly in place of 1 positive 1 over t squared times dt, I can replace dp. So this is equal to integral dp divided by, in place of t negative 1 over t, that's going to be p raised to the power of 2 positive 2. I'm going to rewrite this as integral dp over p squared positive root of 2 raised to the power of 2. Now we know formula. So what is the formula we know? We know that integral dx over x squared positive a squared is equal to 1 over a tan inverse of x over a positive c. So using the formula, this is going to be 1 over a, that's going to be root 2 tan inverse of x over a. Fair enough, right? But my p is actually t negative 1 over t, right? That has to be divided by root of 2. Okay, so that's fine, but my t is actually x raised to the power of x. You see that? So that has to also be reverted. So this is equal to 1 over root 2 tan inverse of x raised to the power of x negative 1 over x raised to the power of x divided by root of 2, positive arbitrary constancy. So this is a good place for us to draw the red line, and this is a beautiful question. So I would suggest that you practice yourself, and perfect practice makes great benefits. So students, having mentioned that, we will move on to the next question. Students, the next question is also a beautiful question. We've been asked to integrate integral cos 2x over sin x positive cos x raised to the power of 2 with the differential operator dx. Now I'm going to, so cos 2x can be rewritten as cos squared x negative sin squared x divided by, now I'm going to write sin x positive cos x as cos x positive sin x. Of course you got to have the dx there. Now the numerator cos squared x negative sin squared x can be rewritten as cos x negative sin x times cos x positive sin x times dx divided by cos x positive sin x raised to the power of 2. Now clearly cos x positive sin x can be cancelled here, and that is going to be giving us integral cos x negative sin x over cos x positive sin x with the differential operator dx. Now you would be tempted to apply the types which I've just mentioned because it's linear in nature, So you would be substituting for cos x and sin x and dx, and making the simplification or performing the simplification. But I would suggest don't do that, because this can easily be solved by substitution technique. If I were to take cos x positive sin x to be equal to t, if I were to differentiate cos x, I get negative sin x. If I were to differentiate sin x, I get cos x, and that has to be multiplied with dx. Now if I were to rewrite this, then you will be able to observe the form. This is nothing but cos x negative sin x times dx, right? But what is this? Differential of t would give us dt. So in place of cos x negative sin x times dx, I can substitute dt. So it's a straightforward, right? So this gives me dt and this gives me t, and integral of dt over t would give me ln t, but my t is cos x positive sin x. So substitute that and add the arbitrary constant c, and this is a good place for us to draw the red line. So this is the nice problem, students. I hope you understood this. We'll move on to the next question. Students, let us do this beautiful question. We are expected to integrate integral of sin 2x over sin raised to the power of 4x positive cos raised to the power of 4x times dx. Now, whenever you have terms like sin and cos, try to convert them into tan. That is the basic idea. So I'm going to rewrite this as, I know sin 2x is 2 times sin x cos x divided by, what I'm going to do is I'm going to divide this quantity sin raised to the power of 4x positive cos raised to the power of 4x. Since I've told you that I would like to convert these terms to tan, I would divide this by cos 4x and I will multiply this by cos 4x. So this can be rewritten. So this is going to be integral. I'll place the 2 out. Now one of the cos 4, in fact I should also place the dx there. One of the cos x can be cancelled here. So I have 2 times sin x with the differential operator divided by sin raised to the power of 4x over cos raised to the power of 4x. So I'm going to write it like this. Positive cos raised to the power of 4x divided by cos raised to the power of 4x is 1. Now I got a cos cubed x, so I'm going to write cos cubed x as cos x times cos squared x. Now I can club sin x with cos x, and that would give me tan x, and 1 over cos squared x is going to give me secant squared x dx divided by sin raised to the power of 4x over cos raised to the power of 4x would give me tan raised to the power of 4x positive 1. Now what I wish to do is I would like to take make the following substitution. Let tan x be equal to t. I differentiate, I get secant squared x dx is equal to dt. Now clearly you can see that secant squared x dx. So just substitute that. So it's going to be 2 times. In place of tan x you got a t. In place of secant squared x dx you get a dt. In place of tan raised to the power of 4x, you have t raised to the power of 4 followed by a 1. Now what I wish to do is I would like to rewrite this as 2 times integral t dt over t raised to the power of 4. I'm going to write it as t squared raised to the power of 2 positive 1. Then I'm going to make the following substitution. Let t squared be equal to sum p. So this is going to be 2t dt is equal to dp. So you have a 2t dt. So this is going to be equal to a dp there, and t squared is equal to p. This has to be raised to the power of 2. So you have a quantity like this. But we know a formula. What is that we know? We know that integral dx over x squared positive 1 is nothing but tan inverse of x over a. In this case it's 1. So because of this formula, this is going to be tan inverse of p, which is nothing but tan inverse of my p is t squared, but my t is tan of x, right? So you have to substitute that. So it's going to be tan of x raised to the power of 2, and that has to be added with an arbitrary constant c, and that is a good place for us to draw red line. So this is in fact a beautiful question which requires some thought process. I hope you understood this, and practice makes perfect. Friends, this is a beautiful question. We expected to find the value of a and b given that square root of cos cubed x over sine raised to the power of 11x times dx is equal to negative 2 times of a times tan raised to the power of negative 9 over 2x positive b times tan raised to the power of negative 5 over 2 times x positive arbitrary constant c. So this is a beautiful question. So foremost I will consider the left hand side. So it's going to be integral root of cos raised to the power of 3x over sine raised to the power of 11x. Now what I wish to do is I would like to bring in tan here. So for that I would have to divide this by cos raised to the power of 11x. That's exactly what I'm going to do. So as I mentioned to you earlier, if you have questions involving sine and cos, you will have to bring in tan, do some manipulation so that you have a tan there, and that is the easiest thing to achieve, or I should say towards the solution. So I'm going to divide this by cos raised to the power of 11x, and I'm going to multiply it by cos raised to the power of 11x. So it's all inside the square root. Now this cos sine raised to the power of 11x over cos raised to the power of 11x, this is actually, now we know that this is tan. Now I got a cos cubed and cos raised to the power of 11x. So what I'm going to do is I can cancel the terms here. So I'm going to cancel here, I'm going to cancel the 11 here. So if I were to do that, I would get 1 over, so let me write this down, 1 over, this is tan raised to the power of 11x, and this is going to be cos raised to the power of 8x. Now 1 over cos squared x is, let me place that, 1 over cos x is secant x, so you have a square there, so this will become squared, so you have a 8 there, this will become 8. So this is equal to integral, of course I need to place the dx there, root of, this is secant raised to the power of 8x over tan raised to the power of 11x times dx. Now I'm going to rewrite this further as root of secant raised to the power of 8x over root of tan raised to the power of 11x times dx. Now this would give me secant raised to the power of 4x divided by, this is going to give me tan raised to the power of 11 over 2x times dx. Now I'm going to rewrite secant raised to the power of 4x as secant squared x times secant squared x times dx divided by tan raised to the power of 11 over 2 times x. Now we know that secant squared x negative tan squared x is equal to 1, so from here secant squared x is equal to 1 positive tan squared x. So I'm going to take, in place of secant squared x, one of the secant squared x will be replaced with 1 positive tan squared x. So this is equal to 1 positive tan squared x times secant squared x times dx divided by tan x raised to the power of 11 over 2, so this is tan raised to the power of 11 over 2x, right? So now what I wish to do is I would like to take tan x to be equal to t, so this would give me secant squared x dx is equal to dt. So this is equal to integral 1 positive, in place of tan x is going to be t squared, in place of secant squared x dx is going to be dt, So this is going to be replaced with t, right? Tan x is equal to t, so this is going to be t raised to the power of 11 over 2. I can rewrite this as 1 over t raised to the power of 11 over 2 positive t squared over t raised to the power of 11 over 2 times dt. This can be further rewritten as t raised to the power of negative 11 over 2 times dt positive integral t raised to the power of 2. I push this is going to be negative 11 over 2. So this has to be multiplied with dt. So over here this can be integrated. This is actually 4 negative 11, right? So that is going to be, let me just place the quantity here, t raised to the power of negative 11 over 2 dt positive, this is going to give me t raised to the power of negative 7 over 2 dt. So I'm going to integrate this. This is going to give me t raised to the power of negative 11 over 2 positive 1 divided by negative 11 over 2 positive 1 positive t raised to the power of negative 7 over 2 positive 1 negative 7 over 2 positive 1. This is going to be t raised to the power of, now when you simplify this you get negative 9 over 2 divided by negative 9 over 2 positive t raised to the power of negative 5 over 2 divided by negative 5 over 2. Now if you were to flip this, you would get 2 over 9 with the negative sign, right? And then you get the t raised to the power of negative 9 over 2 followed by negative 2 over 5 t raised to the power of negative 5 over 2. Now if you were to take negative 2 out, this would give me 1 over 9 t raised to the power of negative 9 over 2 positive 1 over 5 t raised to the power of negative 5 over 2. Now but my t is tan x, so I substitute it there. I get negative 2 of 1 over 9 tan, right, t is tan x, so this is going to be tan raised to the power of negative 9 over 2 with the x there positive 1 over 5 times tan raised to the power of negative 5 over 2 with the x there positive arbitrary constant c. Now if you were to compare this with the original quantity given on the right side, you see that this is compared with this is exactly the same. So in place of a, so this would mean in place of a you get 1 over 9 and in place of b you get 1 over 5. So that is a good place for us to draw the red line. So this is a beautiful question and we have achieved the solution for this question. Thank you students, we'll see you all in the next lecture.